LeetCoding?
Sure. So let me share my screen. Going live. All right. So this is another classic graph problem, and I think last week that problem essentially the n queens problem is a harder version of this kind of pattern of doing a graph traversal. So I think it's fruitful to return to the basics and just essentially examine how to traverse a graph and to clone it. So that would be our task for today. And this problem is because of the LeetCode. It takes a while to get familiar with the LeetCode way of doing things, but I think that's also a very useful exercise to really understand how to shape your inputs that LeetCode gives you and how to understand and interpret them, and then also how to return the result that LeetCode is asking for. So this problem is very weird in that aspect that the inputs and the outputs are not very intuitive to understand. And it's really just reshaping the result so that it would pass the online judge. But I think it's a useful exercise to do because if you ever do HackerRank or LeetCode for interviews, you have to understand the inputs that they're giving you and also give them what they expect so that you can pass the test in the online judge. So the question is, given the reference of a node in a connected undirected graph, we have to return a clone of the graph. So you can see in Python 3 that they give us, they already made a type of a node for us. And if you're familiar with graphs, this shouldn't be too dissimilar. We're given a value for each of the nodes, and then each node also has neighbors. So now we need to understand exactly what the input that they're giving us is. So they're saying that each node's value is the same as the node's index, and they're starting at index 1 instead of index 0. So the first node has value 1, the second node has value 2, and the graph is represented in the test case as an adjacency list. So in this adjacency list, you can see that there's 2, 4, 1, 3, 2, 4, and 1, 3, and each of these are the neighbors for that particular node at that index position. So we can see that in this adjacency list that there's 4 nodes in the graph, and the first node at index position 0 is pointing to 2 and 4, and you can see at this graph it's 2 and 4. The second node is 1 and 3, and you can see that at node 2 that it's pointing to, well, it's an undirected graph, so it's connected to nodes 1 and 3, and then the third node is here, and it's connected to 2 and 4, and the fourth node is here, and it's connected to 1 and 3. So very simple graph, and our task is to return a copy, a deep copy. So we can't just return the graph itself. We have to return a separate graph, but that looks like this. So you can see that this looks like a clone. All the nodes have the same values, and they're directed to the same nodes. So that is a legal clone, but you can see it here. This graph is not a legal clone because the nodes are messed up. So we can't return the same graph, and we have to preserve the relationships between the nodes, and also, of course, the nodes' values 1, 2, 3, and 4. So here's another example. Example 2 is that we have a list within a list. So that just means that we have one node and it's not connected to anything else. It's just by itself. And you can see that in the test case of just the empty list itself, this is just an empty graph. It doesn't have any nodes. And then you can see in this adjacency list, we have 2 and 1. So remember, the node at position 0 has a value of 1, and its neighbor is 2. So that's a lot to keep in track, but that's how this is how they're representing the input as an adjacency list. And you can see that there's a second node at index position 1 that has a value of 2 and is connected to the node of value 1. So if there's any questions in terms of the inputs and the examples they've given us in our task, let me know now, and I'll go ahead to actually solve this problem. So in terms of a graph problem, when you really see this graph problem, I think it's very, we're going to do I've went through DFS multiple times in the past few weeks, and we're going to do another recursive DFS because I think it's always worth repeating it. But our task is really like always think of traversing. Whenever you see a problem like this, we have to traverse the original graph, and then we have to clone it, right? So that's our task. We can't just do a nice traversal of the graph. We actually have to be doing something while we're traversing. So what we need to do is we need to have a mapping between the original nodes and the copy and their copies. So since we're doing recursive depth first search, we always must have a base case. So let me say if there is no node, we just do a simple return. And now we do the copy here, right? So in terms of making the copy, because we're already given the definition of a node, what we can do is I can call this just a copy, and then I could make a node, and then given the input of the node, because, and this is where LeetCode gets, it was confusing for me at first too, so, but what they're giving us is just the first node. So they're just giving us a reference of the first node, and then this first node has a value of 1, but it's able to keep track of everything else because of its neighbors, because it has an attribute, neighbors, and each of the neighbors has their own relationships. And as a result, what we can do is we can actually return the copy of the node of just a single node, but we just have to make sure that their neighbors are in order, and that would actually be our answer. So we don't have to return essentially the whole adjacency list, because in their test debugger, they're just going to look at the neighbors, and they're able to find out if the order is preserved. So it's a little bit confusing, especially also writing in Python, but what we need to do is we're given a reference to a node, and that node has neighbors that are references to the other nodes. So we're not returning, so we don't need to return the whole graph because it already has pointers or references to their neighbors. So now we need to, so we have to do a traversal of some sort, and we have to have a mapping between the original nodes and their graphs. So let me make the mapping right now. I'm just going to call this a map. That's a key word, so I'm going to call it a dict map, a dictionary map, because dictionaries are a very useful way of representing graphs in general, and very efficient way as well. So we're going to call this, so we're going to have the node that is given to us as the key, and then we're going to have a copy as the value. So now we have the mapping between the original nodes and their copies, and now we're going to do the depth first search on it. So what I can do is I can make a depth first search here or as a function. I think I'm just going to make the function separate. But what we're going to do is we're going to do a depth first search, and then we're going to traverse through the node that we're given, and then we also have to pass along the dict map of all of its, so that we can keep adding to the mappings between the nodes and their copies. So now we just need to write the depth first search, and then we're given the node, and we're given the dict map, and then in the depth first search, what we need to do is we loop through each of the neighbors in the node's neighbors. And while we're looping through the node's neighbors, we're also doing the depth first search for each of the neighbors. So you can imagine in terms of recursion, as a review, we're going very deep for one node and its neighbors, and then once we hit the stopping point, then we check the other node's neighbors, and we go deep correspondingly for each of the neighbors in turn. So and then we pass along the dict map. For this problem, though, we care about whether we want to keep adding nodes to the dict map as we pass along the dict map to each of the recursive combinations. So we have to exactly check to see if the neighbor is actually inside this dict map already. And if it's not in the dict map, we keep recursing over. However, if it is, then what we can do is we can just say that the dict map of this particular node as the input, we're going to append the neighbors, and we're going to append the dict map of the neighbor. So this means that the dict map, as you know, we've defined it as the value we're given is the copy of the node, and now to this copied cloned node to its neighbors, and we're appending the dictionary map neighbor copy. So we're building our own separate cloned copied of the graph. And now, so that reminds me that, so that takes care of if the node already exists in the dict map, but in order for it to already exist in the dict map, we actually have to, if the neighbor is still not in our dict map, like in the first few nodes most likely, that we haven't even defined the neighbors yet, so we have to build them up. So in order to build them up, what we need to do is very similar to what we did above here. We could do a copy here, and then we do node, and then we pass along the neighbor's values, name value, and then we have a copy, and then in this copy, we pass along, we make the copy node, the neighbor equals copy, and of course, and it's not merely enough that we found that we're trying to build a neighbor in our dictionary map and making a new additional clone node in our dictionary map. We also have to make sure that its neighbors are in order. So we can do, actually, I think what we need to do is we need to add to the neighbor, the node that we're given, that we found a neighbor because it's not in dictionary map, so we're going to create it, and we're going to copy it over. But I think we need to pass along the copy because I think we can actually pass along the dict map neighbor. Or we could pass along the copy. But either way, we're going to append the neighbor, and let's see if this works. So neighbor is not defined, and neighbor. Let's do that. All right, so it's accepted, and let's submit it. And yeah, it works. So in closing, what we're doing is we're traversing the original graph, and during our traversal, we're using a recursive depth-first search, and inside this depth-first search, we're going to create mappings between the original nodes and their replicas, their copies. And in a depth-first search, where we go through every single node, and for every single node's neighbors, if we haven't already put it in our mapping, we're going to make a copy, and then we're going to construct. We're going to make sure that the neighbors has the right. We're going to make sure that in our mapping that those neighbors have the right copies, and then we're going to continue doing the depth-first search for each of the nodes in turn until we hit the base case and we don't have any nodes, and then we just return the copies. Any other questions besides that?
Edwin, I just have a question. So the use of such knowledge, this is just to get to be good within interviews, or this is related to a specific focus in coding or machine learning, or whatever it may be?
Yeah, that's a good question. What I would say is for all of the above, because these questions are very common in interviews, but recognizing the utility of a graph data structure is very important in software engineering, because you would see that many problems devolve to a graph problem, and knowing how to traverse the graph uh, well is something that is really necessary for in order to make really elegant solutions. Because otherwise, if you didn't know that a graph existed and you don't know how to traverse it, you may be ending up with very hackish solutions. So, like, just to give an example, uh, there's many in terms of whether to check for valid states, whether certain entities, let's say you have a lot of state machines, and you want to check that each of these, like, whether a state machine is in a valid state, it really lends itself well to a graph data structure, and then you can traverse to check if whether that state is valid or not. And because especially if these state machines have relationships to each other, so it does find itself like oftentimes used in industry. So it's not merely like an interview problem or an academic exercise. Does that make sense?
Yeah, I get you. I just maybe because I'm like barely fresh at this stuff, I don't know what a state machine is. So maybe if you can like guide me some more, maybe this when you guys and when you send in the emails out, just if there are like some articles, maybe I need to just to get myself up to speed with the overall understanding of what is a state machine and the use of the traversing of a graph.
Yeah, I mean, to simplify it, so let's say that we have a graph. So let's say we're building a social network, right? And each node is a person, right? And each person has values associated with them. Let's just say it's a very simple value. Let's just say it's an ID, right? So in this, let's see, if you look at this original graph example, let's say we have a group of 4, and I'm number 1, right? And I'm friends with number 2, let's say that's Tom, and number 4, let's say that's Matt, right? Okay. But let's say that you're number 3, and I'm not connected to you, right? Okay. But let's ask the question, am I a friend of a friend, right? Are you a friend of Tom or Matt? And let's say you are, right? So then the graph will look like this, would it not? Right?
Yes.
And then when I'm presenting to you friend recommendations, let's say a very simple algorithm is just friends of friends, right? No crazy AI. We're just going to show, like let's say when I log onto my own social network and I want to make more friends, they're just going to show me friends of my 2 friends, Matt and Tom, right?
Walmart secret.
Yeah, so you can see how we have to traverse this graph, right? Using a variety, like either using depth first search or breadth first search. And then we're able to see that, and then the social network algorithm can return me you, right? And then it'll recommend me you because you're a friend of a friend, right? Does that make sense?
Yes.
Yeah.
So that makes sense, actually. Yes.
Yeah.
Perfect sense.
Yeah. So that's why traversing a graph is very important. So this kind of problem, like cloning a graph, right? Let's say that this social network database has like this data, right? So it has me value 1. It's giving me this adjacency list, right? I'm connected to numbers 2 and 4, to Matt and Tom. And number 2 is Tom, and he's connected to me and you. And then number 3 is you, and you're connected to Tom and Matt, 2 and 4. And then Matt is connected to me and you, right? So let's say that I want to copy this. I want to clone this graphical database. Then you would have to do something like this, right?
Yes.
Yeah. So it is like, it's not just merely an academic problem, but but it's learning how to traverse and also have like cloning a graph, having a mapping between original nodes and their copies. I think finds itself in industry, but obviously like it's not something that you can always like memorize. because you can always look this stuff up in industry, and there's no time pressure. But I think recognizing that this is a graph problem and knowing the basic fundamentals of graph traversal is very important. Does that make sense?
Yeah, yeah, perfect sense. I appreciate the example made it crystal clear, honestly. Yeah, appreciate it. Thank you so much.
Yeah. Any other questions? All right, that's it for me. And I'm always available for other questions.